Simultaneous estimation of two drugs by UV spectrophotometry part 2. The previous video on this topic deals with the basic principle of simultaneous estimation. From that we know we have to determine the lambda max of two drugs and develop standard curve for each drugs at each wavelength. This one is an example. For example, let's assume the name of the drugs are A and B. Scanning showed that maximum wavelength A and B of A and B are 256 and 224 nm respectively. Well, for scanning we have to use pure drug solution and the mixture on to do. And we have to create a series of concentrations, standard concentrations for developing the standard curve. For sake of convenience, we'll take 256 nm as the first wavelength and 224 nm as the second wavelength. We'll use it as 1 and 2. The concentrations will be expressed as X. X stands for unknown. We are going to determine the concentration of drugs. So we have to use the symbol X. And for drug A, the symbol will be XA. For drug B, the concentration will be designated as XB. So 4 standard curves need to be drawn. The standard curve of A at wavelength 1 is designated as YA1 is equal to MA1 XA. Y for the response variable, that is absorbance. A indicates drug A and 1 is the wavelength 1. So YA1 is equal to MA1, M for slope, A for drug and 1 for the wavelength. This is the slope of the drug, standard curve when the measurement was done at the first wavelength for the drug A. So similarly, we have 4 standard curves. One point to remember is the regression coefficient. For every standard curve we have regression coefficient, but if the regression coefficient is very low, it indicates the relationship may have come because of the noise. The apparent relationship is not true. So if the value is low, we may ignore it. So here are our 4 standard curves. YA1, we have a regression coefficient 0.9779. YB1, we have got another slope and regression coefficient. All are close to 1, so we'll consider all 4. And sometimes one drug may not have significant absorption at the other wavelength, and there the regression coefficient will show, it will have a value, it can be ignored. Now look at the final equation. Here we have got Y1. Y1 is equal to 0.1638 XA plus 0.0258 XB. Y1 is the absorbance given by both the drugs. UV cannot distinguish between the drugs. Both the drugs will absorb. Some will absorb more, some will absorb less, and their contribution is given in the individual terms. These terms we have actually taken from the standard curves. So similarly, Y1 will be the contribution of XA and contribution of XB added. Y2 is similarly another equation. that will have the slopes included from wavelength 2. Now, when you actually perform the experiments, y1 and y2 will have real values. These values we have taken as 0.9 and 0.5. Now look at the equation. These equations will have only two unknowns, x1 and x2, and all other things are known. If we can solve these two equations, we will be getting the values of xa and xb. And when xa and xb, these concentrations are multiplied with their dilution factors, we will be getting the quantities. Now 0.9 and 0.5, these are the absorbances. We have to eliminate one term to get the value. To do this, there is an easy method. We can divide one of the slope, that can be A, that can be O, of the first equation with the corresponding slope of the second equation. One thing we have to remember, we have to take the slope of the same moiety. We can take xa or xb, anything, but the slope of the xa should be divided by the second slope of the xa, not that slope of xa be divided by the slope of xb. So by doing that, we got a factor 2.559375, a very long term. It can be reduced, but I intentionally did not do it because this term is going to be multiplied many times and affect the accuracy of the solution. So by dividing 0.1638 with 0.064, we got 2.559375. Now, with this factor, we have multiplied both sides of one equation. And now one term has become same, that can be cancelled. Subtract the equation 2 from equation 1, you get a value that is minus 0.3797 is equal to minus 0.065 xb. Only one term is there, xb. Both have got negative signs, so both cancels out. So from here, simple division will give us the value of xb. We got xb, that is 5.788 microgram per ml. We can substitute the value of xb now in another equation. The first equation we have substituted, and that is giving us the value of xa as 4.58 microgram per ml. But remember, this is the value of the dilute solution. Before measuring, we had crushed the tablets, taken some quantities of the powder that is very small, because Beer-Lambert's law won't be valid for concentrated solutions. So while doing the whole process, we have to keep in mind the dilutions, number of times the solution has been diluted. So these are the values of the diluted solutions. We have to multiply this with the dilution factor. I have taken the dilution factor as 10,000. So multiplying that, I get a huge value, 45,830 microgram. But this unit is microgram. Divided by 1,000, it becomes milligram. Similarly, for xb also we get the quantity in milligram. And these are the quantities that actually has been taken for estimation. It can be 100, it can be 110, whatever the quantity by difference, you do not get the exact round figure, but we have to note it down. These are the quantities present in that. Sometimes due to error, the quantities may be slightly more. Without bothering about the accuracy too much, we have to see whether the amounts are within the overages. In tablets, most of the times there are overages. Companies deliberately add extra. So this is the quantity, and multiplying it with a factor, that is the actual, we can get the actual quantity present in a tablet. There were lots of disturbance in this. This is done in a common room. Sorry for the disturbances.